Hi, we continue this chapter talking about the continuity of a real function. We define the continuity of a function at a point by the following. If f is a function defined on I, that is included in R of course, taking values in R, and if x0 belongs to I, this is very important, then we say that f is continuous at a point of x0 if the limit of x when x tends to x0 is equal to f of x0. What does it mean? It means that if you have a function, then this function, if this function is taking a value at a point x0, then if you approach x0 from the left side, the images will be approaching f of x0 from the left side. You see the images? They are approaching f of x0. And if you are approaching x0 from the right side, the images of the function will be approaching f of x0 from the left side. If these properties are satisfied, it means that f is continuous at the point x0. But when f is not continuous, it's not continuous if this is not true. What does it mean? It means that if you have a function, for example, that takes a value f of x0 at x0, then this function, if you approach x0 from the left side, the function will approach f of x0 without any problem. But if you approach x0 from the right side, the function will not approach f of x0. It will come, for example, in here. So the value of, or the image of x0 is in here, and the point in here is void, so you don't have an image for x0. But right next to x0 on the right side, you have an image in here. So if you have such a function, we say that it's discontinuous or it's not continuous at this point. And you have this jump between f of x0 and the image of any number on the right of x0, even if it's too close to x0. For example, if I take the function 1 over x, can we say that it's not continuous, it's discontinuous at 0? Or can we say that the function overall is not continuous because it has two parts? That's wrong, because at the point x0, we don't talk about a discontinuity, because the point x0 equals to 0 is not a point in I, it's not in the domain of the function. So we talk about discontinuities at points within the domain of the function. So this function is continuous even though it has two parts. You can have a function that is partitioned into 10 parts and it's still being continuous because it doesn't have this continuous point or the discontinuity point, because we don't have any point in the domain where the function is making a jump. So here you can see the jump made by this function, so it's discontinuous. And here, if the right part and the left part are joining them each other at the same image f of x0, then the function is continuous. We have another case or shape of discontinuity. If the function is making this, it's approaching a number in here and it's approaching the same number in here, but at this point x0, the image of the function is in here. So here it's a void image, void number. So it's right that the function from the left and from the right side of x0, it's approaching the same number, which is this one, but the image of x0 is somewhere else. So here also we have a discontinuity. Now we can have many results related to the continuity. First, if f is continuous at a point x0, then f is bounded in a neighborhood of x0. So if it's continuous, then it's reaching the point x0, f of x0, right? So if it's reaching the point x0, f of x0, then you can take a neighborhood of x0 where the function is bounded and it cannot go to infinity, because if it's going to infinity in here, you can take a smaller neighborhood where the function is bounded. so it's bounded in a neighborhood of x0. There exists a neighborhood where the function is bounded. Now if it's continuous at any point of the domain, it means that the function is globally continuous, and we say that it's continuous on I if it's continuous at each point of I. Now the images that I drew before, for example this one, that says that the function it's approaching x0, f of x0 from the left side but not from the right side, it means that this function is continuous from the left but not from the right, because from the left it's approaching the image of x0 but not from the right, and also it can be right side continuous without being left side continuous. So if it's left side continuous and right side continuous, then it's continuous. Therefore, if it's continuous at x0, it's equivalent to saying that the limit from the right equal the limit from the left equal f of x0. And now, of course, since we have the properties that we proved with the limits, and since continuity, it means that the limit from the right is equal to the limit from the left, it means that if you have f and g, two numerical functions defined on an interval a continuous at x0, then f plus g, lambda f times g are all continuous at x0, and also f over g if g of x0 is not equal to 0. And this is due to the definitions of the limits, or the proofs that we made using the definition of the limits in the theorem on the limits, on the algebraic operations on the limits. Also, using the theorem on the limit of a composite function, we can prove that if f is continuous at a point and g is continuous at the image of this point, then g round f is continuous at x0. Now, suppose that you have a function that is approaching a number in here and approaching the same number from the right side, but the image of this point is either not existing or it is somewhere else. Okay, so it can be not existing or it can be defined somewhere else. Then we can define a new function that is exactly equal to this function everywhere, except that at this point the image of the function is equal to this point, which means it's equal to the limit of the function when x tends to x0 from the right, and it's equal to the limit of the function when x tends to x0 from the left. So it's equal to the right and left limits at x0, which means that we are putting a point to ensure that the new function we are defining will be continuous. So whether we replace the point that's in here, or if the point is not defined, is not in the domain, we are adding this point to the domain of the new function we are defining to have a function equal to the other one everywhere and continuous at this point. So this is what you call the extension by continuity. So if you have I an open interval of R and A belongs to I, if f is a function defined on I except at a point A, and also it can be defined somewhere else, but usually it's interesting when it's not defined at a point A, then if the limit of f of x is equal to L, it means that the limit right and the limit left are equal to L. Then we define a new function g of x that we write as follows. We say that g of x is equal to f of x when x is not equal to A, so it's equal to f of x everywhere. And at the point A, it's equal to this limit L. Then this g of x is defined as the continuous version of f, and we call it the extension by continuity at A of the function f. So we say that f has an extension by continuity, which is g. So in order for f to have an extension by continuity at a point A, you should have the limit right of f at this point A equal to the limit right of f at this point A. And this limit will be defined as the image of A with the extension by continuity. We give now some results on the continuity of a function on an interval and on a segment. First, the intermediate values theorem. In fact, the continuity of a function is something very interesting because it allows us to have very interesting properties. If you have a function f that is going from a point A, or f of A, to a point B with f of b, right? Then if it's continuous, we are sure that it takes all the values between f of a and f of b. So if f of a, for example, is equal to 5 and f of b is equal to 10, then for sure a number between 5 and 10, let's say, I don't know, 7, it has a pre-image in here. So for a number that you choose between 5 and 10, it has a pre-image, then there exists a number in the domain such that its image is 7 or it's 8 or it's any number between 5 and 10. And this is only correct when the function is continuous. So if you take I as being an interval of R and f continuous mapping such that f of a is less than f of b, so of course you will have one of them less than the other one, then f takes at least once all the values between f of a and f of b. So whatever number gamma that you choose between f of a and f of b, you will always be able to find a point C in the domain such that f of c is equal to gamma. This intermediate values theorem is interesting when the gamma that you have in here is equal to 0. So if you have, for example, f of a and f of b, two numbers such that one of them is negative and the other one is positive, then 0 is a number between f of a and f of b. So 0, it has a pre-image. So there exists a number c such that f of c is equal to 0. So there exists a number c that is a root to the function because f of c is equal to 0. So again, this is particularly interesting when the function takes somewhere a negative value and a positive value, which means that there exists a number such that the image of this number is equal to 0. And this root can not be unique or can be unique. It's unique when the function is monotonic. So if the function is taking a negative value and a positive value, then there exists a point where the function is equal to 0 and this point is unique. And also you can have this case scenario if the function is making like this. So it's taking a negative value and a positive value, and you have multiple roots in this case because the function is not monotonic. We can prove also using the intermediate values theorem that the image of an interval by a real continuous mapping is an interval. So if you take 2 points A and B and you take the image of the segment AB, so the image of all the points between A and B, you will have an interval as the image set. Why an interval? Because an interval is something, is a set such that if you take 2 points in this interval, any point between them is within the set. So if you take 2 points in this image, then any point between them has a pre-image. So it's in the set because it has a pre-image between A and B. So that's why we can prove mathematically, we can write it correctly, that the intermediate values theorem is equivalent to saying that the image of an interval is an interval. So we can write now properly the following. So if we have AB belongs to R2 such that A is less than B, then any function defined from the segment AB, so it's an interval, the segment AB into R, if f is continuous and bounded, then it will reach its boundaries, which means that the supremum of f of x and the infimum of f of x for x between A and B exist. And they are images to two elements y1 and y2 in this case. So to understand this, let me take this example. If you take 2 points A and B and then you define the function f that's making like this, so f of b is in here, f of a is in here, then f has a maximum in here and a minimum in here. It's reaching these two maximum and minimum, so there is a point in here whose image is the maximum and a point in here whose image is the minimum. Now be careful, I took this example to show you that if f is going from AB into R it doesn't mean for sure that the maximum and the minimum of f on AB are reached at A or at B. So you see here f of A and f of B are in here. They are very close to each other. So they are very far from the maximum and the minimum. That's why the maximum and the minimum of the function on AB are two values reached at some given points that are of course between A and B, but they are not necessarily A and B unless the function is increasing or decreasing. If the function is increasing, then the maximum is at f of B and the minimum is at f of A, and if the function is decreasing, the maximum is at f of A and the minimum is at f of B. So also, if we take the same result that we obtained for the intermediate values theorem and we write it on a segment AB, it means that if you have a segment AB such that f of A times f of B is negative, it means that f is taking a negative value and a positive value, then there exists x0 such that f of x0 is equal to 0. So x0 is the root or a root for the function, and this root is unique when the function is monotonic. And also what we already said as well for the intermediate values theorem, the image of a segment AB is a segment in R. So if you have AB a segment, the image of AB is MM, where small m is, as I showed you on the figure, is the infimum and big M is the supremum. So more interestingly in here, we have any point between the inf and the supremum of f when x belongs to AB has a pre-image. So not only the points between f of A and f of B, but also all the points between the infimum and the supremum. So if your function is doing this, then this is A f of A and this is B f of B. Okay, then this is the supremum and the minimum. Any point between the supremum and the minimum has a pre-image. And to finish, we define the inverse function of a strictly monotonic function. So if you have a function f defined from AB into R, continuous and strictly increasing, then f is a bijection, of course, that goes from AB into f of A, f of B. So f of A in here is the minimum, f of A is the maximum, or the infimum and the supremum. Then we can define an inverse function that is also strictly increasing and continuous, and that goes from f of A, f of B into AB. So this inverse function is a function that does the inverse of f. So if you have a point 2 whose image is 5, then with f minus 1, the point 5 has an image equals to 2. So this function will inverse the roles of the abscissa and the ordinates, the images. This is also true when the function is strictly decreasing, because it will be also a bijection, but watch out here, f of A B will be f of B f of A, because f of B will be the minimum or the infimum and f of A will be the supremum, and f minus 1 will be also existing from f of B f of A into AB. And since f minus 1 will be inversing the roles of x and y, then the graph of f minus 1 will be symmetric with respect to y equal x to the graph of f. So if you take y equal x, if you have a function doing this, then this point has this image. So in f minus 1 you will have this point having this image, so it will be symmetric with respect to y equal x, and the function will be like this. Of course, both functions will intersect at y equal x. And so this is how we define the inverse function.